In this video, the Texas grid model will be used to demonstrate a dynamic equivalent network reduction. Study case 8.1 should be activated. The network reduction command dialog is accessed from the additional functions toolbox, here. For load flow or short circuit calculations, a static equivalent network reduction is suitable, and a video showing the basic principles of this network reduction using the standard transmission system example is available. However, if the reduced network is to be used for RMS simulation calculations, a more sophisticated approach is required to ensure that the dynamic behavior of the reduced network is very similar to the behavior of the original network. On this basic options page, the boundary for reduction has been specified, and we see that everything outside this boundary is to be reduced. To visualize this, we can mark the interior region, which will be retained, on the geographic diagram. We can see that a large part of the network will be reduced. Here, the load flow command and simulation command dialogues can be accessed. From the initial conditions dialog, we see that the event to be analyzed is the loss of a synchronous machine, 2013. The dynamic network reduction consists of two steps. In the first step, a simulation is carried out to analyze the response of the generators to be reduced to a disturbance on the network. Using the results of this analysis, they are then aggregated into groups according to coherency criteria. Each group will then be replaced by one or more equivalent generators, with the behavior of the rest of the network assumed to be static. In the second step, the network is then reduced using the standard REI network reduction process. Let us look at the options on the dynamic equivalent page. The Coherency tab offers options relating to the first step. The disturbance to the network can be in the form of a generalized noise signal, or an existing event. Here, the previously specified event at generator 2013 will be used. The coherency identification method is selected, and in this case it is based on correlation coefficients, with the default threshold of 0.8 being specified. This is a good starting point. With a lower value, fewer equivalent generators would be created, but the accuracy could be compromised. The option selected here ensures that only machines with the same control mode, such as constant V or constant Q, will be aggregated. So unless all the generators in any particular group have the same control mode, the group will be represented by more than one replacement generator. On the Controllers tab, the user selects the controllers to be used for the equivalent generators. Should greater precision be required, parameter identification could also be used to tune the new controllers. On the verification page, options have been selected that will let us see how closely the results in the reduced network compare with those in the original network. We have chosen to monitor generator 2123, which is close to the fault location. Now let us execute the command. In the output window, we see that the 420 generators in the reduced area have been aggregated into 7 groups. Let us look at the synchronous machines in a network model manager. We can see the 11 new generators that have been created to represent the 7 groups. On this plot page, the comparison plots for the monitored generator shows that the behavior of the reduced network is close to that of the original network. Looking at the geographic diagram, we can see the reduced area indicated. The changes are held in a network variation, so the initial state is easily restored by reactivating the original study case.